For every twice differentiable function f from real number to minus 2 to 2 close bracket with f of 0 square plus f dash 0 square is equal to 85. Which of the following statements is or are true? This is a multiple answer correct question and we have to evaluate every option to know which of the following options are true. Now, the first option is there exists r, s which belongs to real number where r is less than x such that f is a 1, 1 on the open interval r, s. This is a general property and which is true for every continuous function. That implies A is true. Now we evaluate B option. It says there exists x0 which belongs to minus 4, 0 such that f dash x0 mod is less than equal to 1. For that, by using Lagrange's mean value theorem, we have there exists some f dash c which is equal to f of b minus f of a divided by b minus a. If we consider a continuous function which is continuous from a to b, and which is, so we consider this as continuous in a to b and differentiable from a to b. Then we consider that there exists a c which lies between a and b such that f dash c is equal to f of b minus f of a divided by b minus a. Here we have b as 0. Here we have b as minus 4. Let's take b as minus 4 and a as 0 because we need to find out x0. It's given that x0 belongs to minus 4, 0. Okay. That implies we have f dash c is equal to f of minus 4 minus f of 0 divided by minus 4 minus 0. Now, we know that f of minus 4 will lie between minus 2 to 2 because it is given in the question that it's a twice differentiable function from real number to minus 2 to 2 close bracket, and we also know that f of 0 will also lie between 2 and minus 2. That implies if we subtract both, then f of minus 4 minus f of 0 will lie between minus 4 and 4. Putting the value, we get b. We have f dash c is equal to f of minus 4 minus f of 0 divided by minus 4 minus 0. Then we have the mod of f of c is equal to mod of f of minus 4 minus f of 0 divided by minus 4 minus 0. And we found that f of minus 4 minus f of 0, the value lies between minus 4 and 4. Applying that value, we get f dash c mod always is less than equal to 1, because 1 and minus 1 are the extreme values of f dash c. Hence, we see that option B is true. Now, for evaluating option C, we have limit x tends to infinite f of x is equal to 1. To do that, we have, let's take an example. If we find a function which satisfies the equation that is given, that is f of 0 square plus f dash 0 square is equal to 85, but doesn't have a limit when x tends to infinite, then we can prove that statement C is false. We take f of x as, we take a periodic function, then we can easily prove that the limit doesn't exist. For that, we will take f of x as, we have to do a bit of hit and trial in this to see if it exactly fits the equation or not. We get f of x as 2 sine of root 85 x by 2. We can prove that this function satisfies the equation as, we have f of 0 as 0 and we have f dash x is equal to 2 into root 85 by 2 into cos of root 85x by 2, and f dash 0 is equal to root 85, and we have f of 0 square plus f dash 0 square is equal to 85. So it satisfies the given equation, but we see that limit x tends to infinite f of x doesn't exist. That implies option C is false. Now we have the fourth option, which is, there exists alpha from minus 4 to 4 such that f of alpha plus f double dash alpha is equal to 0 and f dash alpha is not equal to 0. For that, we take a function h of x. We define a function h of x which is equal to f of x square plus f dash x square. then we know that according to the question, h of 0 is equal to f of 0 square plus f dash 0 square, which is equal to 85. In option B, we found that there exists some C which belongs to -4 to 0 such that f dash C mod is always less than equal to 1. That implies f dash C square is always less than equal to 1. This we know from what we have found out in option number B. Hence, we have h of C is equal to f square C plus f dash C square, which is always less than equal to 4 plus 1, which is less than equal to 5. We take this as 4 because the function value always lies between -2 to 2. So the 4 is the maximum value of the function that we can get here. If we assume that there is some p which belongs to -4 to 0 such that h of p is equal to 5. Now, we can do the same thing from 0 to 4. We assume again that C1 belongs to 0 to 4. Then we have h of C1 is equal to f C1 square plus f dash C1 whole square. Now, from the Lagrange mean value theorem, we know that f dash C1 mod is less than equal to 1. That implies f dash C1 square is always less than equal to 1. So, we have h of C1 is equal to f square C1 plus f dash C1 square is again less than equal to 4 plus 1 is less than equal to 5. We assume some q which belongs to 0 to 4 such that h of q is equal to 5. Then we can apply the Rolle's theorem between p and q. Applying Rolle's theorem, between p and q, we get there is some C, let's take it as C2, which belongs to P and Q such that H of C2 is equal to 0. Then we have H of such that H dash C2 is equal to 0 because that is what the Rolle's theorem says. Now H dash C2 is equal to we'll first write how we defined h of x. H of x is equal to f of x square plus f dash x square. Then h dash x is equal to 2 f of x into f dash x plus 2 f dash x into f double dash x. That implies h dash x is equal to 2 f dash x whole f of x plus f double dash x. Now we have h dash of C2 is equal to 0. C2 belongs to P and Q, and P and Q belongs to minus 4 to 4. So we can say C2 belongs to minus 4 to 4. And we have 2 f dash C2 into f of C2 plus f double dash C2 is equal to 0. And we know that f dash C2 is not equal to 0. That implies f of C2 plus f double dash C2 is equal to 0. That implies B is true. So the final answer is the options which are correct are A, B and D.